Okay, we are live with our third live streaming webinar. Thank you very much for joining us. My name is Josh Colchester. I run the Systems Innovation website. Today we are talking on the topic of complexity theory. We're going to explore the key concepts and I'm going to walk you through those. We'll get into those in a minute. So if you have any questions or comments, you can put them in on the sidebar on the right-hand side. I'll get to those at the end. The presentation should be about 40 minutes. We've got a lot of stuff to cover, actually. This is a really big topic. I'm excited to present it to you. What qualifies me, I've been teaching this for about 4 or 5 years now, complexity theory and all its related subjects, systems thinking, network theory, so on and so forth. We've got many courses on it and its application also. So I actually came across it from coming from mathematics. I studied mathematics for many years. I'm pretty passionate about that. And I came to complexity theory from there as a way to help me understand large complex networks. And I spent a few years studying it before I started teaching it, and have been doing that for the past 4 or 5 years. And to be honest, I've done a lot of the learning about it as I've done teaching. Teaching is kind of the best way to learn about things. But what I'm going to present here, as we'll see, is kind of the model that's, or it's not a model, it's a schema that we've evolved for giving some structure to this kind of mass of different models and different ideas. This is what we're going to be covering in this presentation. So we're going to start off there in the middle with complexity theory and complex systems. We're then going to talk about self-organization, nonlinear systems, network theory, and then adaptive systems and evolution. So you don't have to take notes. We're actually going to give you, we've created a guide for to help you learn complexity theory or to teach it. I'm going to put a link below this video so you can just click on that and get the PDF. It'll have this schema. It'll have everything we'll cover in this presentation. So you'll have it all there. Okay, let's get started. So what is complexity theory? It's a set of models for understanding and analyzing complex systems. So it's a set of what we'd say mathematical models. So it's a modeling framework, a mathematical modeling framework that's going to help us understand complex systems. So I say mathematics and you probably think of something like this, the kind of stuff you learned at school, numbers and algebraic expressions and so on. We're talking about slightly different mathematics here. It's kind of a slightly more advanced, maybe you might call it higher mathematics. What mathematicians do, they don't spend all their time figuring out those kind of equations or playing around with numbers. What they do looks a bit more like this, and kind of the best way to understand it is more as kind of a science of patterns. Mathematicians are interested in patterns, really. This book, The Science, Mathematics, The Science of Patterns, presents it quite well. They say to most people, mathematics means working with numbers. But this definition has been out of date for nearly 2,500 years. Mathematicians now see their work as the study of patterns, real or imagined, virtual or visual or mental, arising from the natural world or from within the human mind. So you're going to see we'll be talking a lot about patterns in this presentation. And it's really the best way to kind of understand what we're trying to do here. We're studying a complex form of pattern, and they're in contrast to more simpler patterns. So that equation we looked at, that's very useful when we want to understand some quite simple pattern out there in the world. For example, this mechanical physical system we see on the right. So that's a pulley with a weight, and it just has a few parameters, really, maybe 3 or 4 or so, and you could use an equation like that expression on the left to describe that. But complex systems, what we want to do here is describe more complex patterns, things that look like this. And we have an intuition that that kind of mathematics, those simple equations, are not going to help us here. We're going to need something different. So complexity theory is really the mathematical modeling of complex patterns. And just over the past few decades, we've really, scientists in many different areas have kind of started an endeavor to try and understand more complex patterns. And we call those complex systems. So complexity theory is the study of complex systems. What is a complex system? We'll dig into that now, but we can see here on the right, this is a complex system. It's the urban network of India and Pakistan. But we can see straight away that that pattern there is highly complex, right? We're not going to have any kind of equation, the kind of things you learned in school that are going to describe something like that. We're going to need different kind of models to understand complex, intricate, kind of almost kind of organic patterns like that. They're not very orderly and predictable and so forth, as we'll see now. But what is a complex system? Let's dig into that. So it's a system. A system is a set of parts with the relations between those parts that interconnects them into a whole, makes them interdependent in a whole system. So complexity turns out to be a very fundamental feature of our universe. It's not superficial in any sense. That's why we have a whole science dedicated to complexity. We wouldn't otherwise. And there's really just two types of systems: simple systems and complex systems. Systems evolve from being simple to becoming complex. And a complex system has the properties of having many parts with a high degree of interconnectivity between those parts. There's also a high degree of interdependence between those set of parts that have a degree of autonomy. The individual parts have a degree of autonomy and sometimes adaptive capacity. So when you see a system that has all those properties, you can call it complex. And if you look at all the complex systems we'll talk about during this presentation, or out there that you see in the world, they'll have those features. Many parts, interconnected, they're interdependent and relatively autonomous. So this is a complex system. Very good example, I think. It's a city, it's Bangkok in Thailand. And I mean, straight away we get an intuition that that thing's pretty complex, right? We can see there's many different systems. They're obviously interconnected and they're interdependent, and they're also relatively autonomous and adaptive also. So straight away we can see a transport system, but there's also a water system there. There's obviously, there's going to be a financial system, there's a commercial system, cultural system, political system, many overlapping and intersecting networks that are interconnected, interdependent, dynamic and adapting, but they're interconnected, but they'll also have a degree of autonomy. So that's a complex system. This also is a complex system. It's such an element within a broader complex system. So this is a boat carrying freight, but it's just one element in this kind of vast network of the global logistics network. Well, many overlapping and intersecting networks of different agents. So you take any of those supply chains, you can have many different individuals and organizations, producers, consumers, financiers, commercial entities, so on and so forth, and they're all interconnected and interdependent in that supply chain. And this whole global supply chain at the end of the day. So that's those are examples of complex systems. Complexity theory then is, as I say, a modeling framework to help us understand those complex systems, or the dynamics or features of those complex systems. So we've already said a complex system is a type of system that has the properties, has those properties we listed. The systems that have those properties then have special features or special dynamics, or they exhibit certain behavior, and that behavior, well, one of them is self-organization, but they also have a network structure. They exhibit nonlinearity. They evolve over time. So network theory is trying to really describe those the behavior of complex systems, which is different from a systems that are simpler, right? So if a system has less parts, if it has lower connectivity or interdependence, it won't have these this behavior, these features of the complexity theory is trying to describe. So Self-organization is one of those. It's a very, very important one. It describes how order emerges within decentralized systems, systems without centralized control, where there are many parts distributed out. So an ant colony is a very good example. There isn't a master ant telling everyone what to do. The order emerges out of local interaction. So this is a very good paper, actually, The Science of Self-Organization, Adaptation. I'd highly recommend this to you. It's an excellent little paper that describes quite clearly the basic aspects of self-organization, and we're going to grab our definition from there. So self-organization can be defined as the spontaneous creation of a globally coherent pattern out of local interactions. So, spontaneous creation of a coherent pattern out of local interactions. So, self-organization is about organization. It's asking, how does order emerge in complex systems? So, order, scientists are inherently interested, us as human beings, but particularly scientists, we're interested in order in the world. We're not particularly interested in things that are random, actually. We're interested in where we see patterns, where we see correlations, and we can see in this image on the screen, that system is obviously ordered, right? It's quite clear. But we know that didn't happen by itself. We know someone came along and they imposed order on that system through information, through importing energy to the system. We got that highly organized system. And we see that kind of order all around us in the world that we built. We design systems and then we impose order on them, such as a building. But that's not how order emerges in decentralized systems, because there is no centralized entity that's coordinating everything else. So this is a flock of birds. And we can see quite clearly there's obviously many parts. It's a complex system, many parts. They're interconnected, interdependent, and relatively autonomous. But there's no one orchestrating that whole thing, right? We know there isn't someone telling them what to do. But at the same time, we can see there's order in that. It's not perfectly ordered, but it's certainly not random. So we're interested in where that comes from. And that kind of order is self-organizing. And as it said there in the description, it comes in the definition of self-organization, it comes out of the local interactions between the parts. So scientists have studied this kind of system, this flocking behavior with birds, and they now have simulations for how it works, little algorithms for the agents in the system. So those birds, each bird is just operating under 4 simple rules, where it's following its neighbor or pointing in a certain direction out of that local interaction with its neighbor, all of them responding just to their local interaction, the simple rules that they have, we get this emergent overall coordination and pattern of organization, and that's self-organization. So that self-organization is also emergence, is the general word we use. Emergence describes a very general process of creation that we see in the world, and self-organization, I'd say, is a more coherent set of models around how that happens. And I think this here, people crossing the street, is one of the best examples of self-organization. So we can see here that there's people crossing from either direction. It's actually pretty random at the moment, but quite shortly they're going to meet each other, right? And they're going to have to navigate their way around each other. And what we see empirically, what we see happening in these situations is, right, those people at the front, they kind of navigate, they negotiate with the people coming from the other direction where they're going to go. But once someone has done that, then other people could just follow that person because they've already created a direction, created a little pattern. People behind them find it easier just to follow them and create a stream of people so that they don't have to renegotiate it each time with the people coming from the other direction. It simplifies things greatly. And what we end up with then is maybe two streams, 1, 2, or 3 different streams where people are crossing from one side of the street to the other, and they follow the stream, they get in line with the stream to make it easier for them to get across. And that creates an emergent pattern, right? That system has actually organized itself into a particular pattern. So as a system that's transitioned from initial disordered state, what we see here at the moment, that's very disordered, but in a minute it will have organized itself into a number of distinct patterns for crossing the street, a number of distinct lines or streams, which is a more organized state. So it's transitioned, we'd say, from an initially disordered state, what we'd say a high entropy state, relatively random, to a more orderly state, a low entropy state, through local interactions, right? There was no one actually standing there in the middle telling everyone where to go. They were just responding to the interactions with other people locally around them. And that's self-organization. It's a good example. It shows you also how self-organization is, as I just said there, like more formally, is described as a transition from a high entropy to low entropy, kind of from unorganized to organized. And we can see, well, one feature of it is that it requires high entropy at the beginning. It requires that the system is unorganized. If it's initially in an organized state, it's not possible for it to self-organize if there's already a pattern imposed upon it. And that's a really interesting feature because it says how that order kind of emerges out of disorder. Like that's part of what the models and the equations are actually telling you when you say you're going from a high entropy to a low entropy state, and that you actually need that disorder originally. It's a very interesting dynamic, and Ilya Prigogine presents it here. Ilya Prigogine was he won a Nobel laureate for his work in this field, working with chemical reactions and self-organization, dissipative systems, and so on, back in the 20th century. But he puts it like this: entropy is the price of structure. We grow in direct proportion to the amount of chaos we can sustain and dissipate. So entropy is the price of structure is kind of the main piece there, that self-organizing systems need entropy. They need a disorderly state at the beginning to be able to then self-organize. So it's order out of chaos, as Ilya Prigogine would have said, which is pretty fascinating because that's not normally the way we think about things. We actually normally think of kind of order and chaos as two separate things, but here he's saying that actually they're kind of two sides of the same coin, or they need each other. So this is how self-organization works in practice. We have to have autonomous agents, autonomous elements, like we said, that's one aspect to complex systems, in this case, people operating under their own motives and agendas. So that's the idea that they can't be constrained. They have to be able to do their own thing. Like those people crossing the street, right? They had to be able to choose according to their local information. Same for the birds. And then you also need a lot of interactions, peer interactions. Interaction and information need to be flowing horizontally, not vertically. So it can't be information coming from a single source, a centralized entity. It has to be peer interaction. You then get attractors, network effects driven by positive feedback creates attractors. We'll talk a bit more about this later on, but that's a key aspect. And then you get emergence, the emergence out of those attractors. Like you said, what those people crossing the street, when someone started to create one of those streams, well, that was an attractor for others to follow them because it was an easier path for other people to follow. And the more people that followed, the easier it was for other people to then follow, which is a positive feedback loop, creating an attractor. And out of that, we got the emergence of a global pattern of organization from local interactions only. So that's the basic dynamics of how self-organization works. And it's not magic. We can see in this example, this is called Bernard's cells. It's it's an often cited example of self-organization. You get on the right here, we can see a cylinder or a container of water being heated from below. And what happens is the molecules at the bottom, because they're being heated, they want to rise up. But the ones at the top, because it's cooler there, they want to sink down. And it's just like those people crossing in the street. They have to negotiate where they're going to go. And they create the same kind of, well, it's the same kind of dynamic, but at this time they create kind of cells where the hot ones go up on one side and the cold ones come down on the other. And that's a form of self-organization in a chemical system. But we can see how that order arose because of the input of energy, right? It's not, order costs something, and the system can't just organize without there being an energy source input somewhere. So it has to be a system that's driven by some input of energy. So it's not magic, it's just that the system is being able to, out of its local interactions, turn that energy into a form of organization. Okay, so nonlinear systems. We'll talk about feedback, chaos theory, and nonlinearity. So nonlinearity, what is it? Nonlinearity describes a relationship between the parts that is non-additive, resulting in a combined organization that is greater or less than the sum of the separate parts. So it's that term in the middle, non-additivity, that the parts don't add up to the whole, is kind of central to nonlinearity, and that actually comes back to this feature of nonlinear of complex systems that we mentioned, this property of interdependence. It's a very big idea in complex systems. It's actually a lot of this nonlinearity comes from the interdependence between the parts, and we call those interdependent synergies. And it's the synergies that create relationships that makes the whole different from the parts. It's actually the relationship between them is adding something or subtracting something, and that means the whole is different from if we just had those parts in separation. So there's interdependency and there's synergy. I'll demonstrate how that works now. So this is a flock of birds. I'm sure you're aware they're organized in a particular way to reduce the drag on them as they fly, so they have to exert less energy. And we can also see that they're organized in a particular pattern so as to be able to do that. So if we took each of those birds separately, they weren't in this pattern or organization, and they flew, they would have a certain drag and they'd have to exert a certain energy. So we could sum up each one of those in separation and say, okay, what's the total drag here? What's the total amount of energy exerted? And we'd get some figure. Now we put them into this configuration, and we know that actually the drag on them is going to be less in this configuration. They're going to have to exert less energy to stay flying forward. So when they're in this particular configuration, the whole is going to be, the drag on the whole is less than the sum of parts in isolation, which is interesting. That makes this system nonlinear. And why is it nonlinear? It's nonlinear because of the relationship between the parts. They're configured in a specific way. Right? It's not random the way they're flying. And there's actually a synergy there, right? And there's an interdependence too. If one of those birds moves out, well, that's going to affect the other birds, and it's going to affect the drag on the whole system. And that's very different from having the parts in separation. If they weren't in that configuration, if you had them separate, then they wouldn't be interdependent. So you can see the nonlinearity derives from the interdependence between the parts and the synergies between them. That in this case is reducing the drag and reducing the amount of energy that they have to exert. So that's nonlinearity, but when we're looking at it over time, it becomes about these feedback loops, positive and negative feedback. So we don't have to worry about negative feedback here because that's linear. It's all about this positive feedback when we're talking about nonlinear systems. So positive feedback means one thing creates more of another, which feeds back to create more of the first. A good example is compound interest. So if you have money in your bank account, that will create interest, and that interest will add more to the amount you have in your account, which then will create more interest, which will add again to that, and there's a positive feedback. More is creating more. And that creates nonlinear process of change. It's an exponential process of change because it's compounding, it's feeding upon itself. Hurricane is a very good example of this. It's a nonlinear system. It's a what Ilya Prigogine would have called a dissipative or far from equilibrium system. So I looked in New Scientist about hurricanes, and in their introduction, they said they described the process of the formation of a hurricane in terms of positive feedback here. So when the warm column of air from the sea surface first begins to rise, it causes an area of low pressure. This in turn creates wind as air is drawn into the area. The wind drags out more moisture-laden air from the sea surface in a positive feedback process that swells the storm. So we can see how more is creating more. In this case, the energy and resources driving this hurricane, but we all know that that hurricane is it's a non-normal, it's not a normal occurrence, and it's also an unsustainable occurrence. It's dissipating massive amounts of energy, and it's going to drive itself to extinction. So another example of that positive feedback is when we have bacteria in a petri dish like this. We give them some food, they'll reproduce, and then those offspring will consume the food and they'll reproduce, and that's a positive feedback because the more the population is, the more they can reproduce, the more there'll be of the next population, and so on. And what we know about this is that that population will grow exponentially, but then they'll obviously crash, right? They'll run out of food. So, and that will take them into a new regime. And that creates this idea, well, that leads to this idea of a phase transition, that actually positive feedback, a nonlinear process of exponential change, are inherently unsustainable, and they signify a phase transition, which is a regime change from one state to another. So in that petri dish of bacteria, we started off with maybe no bacteria or few bacteria that were in a stable state, but then when we gave them food, right, we got that positive feedback loop, exponential change, and the system grew hugely, but then crashed and ended up in a new regime. So that's we can say that's a phase transition. We also see that in water, is the best example. We increase the temperature, and that's kind of an incremental process. We increase it maybe 1 degree at a time, but then we also get this phase transition as it goes from a solid to a liquid, and that is a discontinuous process, right? It's actually a regime. It's a change in the whole regime of the system as it goes from a solid to a liquid. A solid is a very different physical regime to a liquid. You can crack ice. It could be ice in this case. You can crack it, but you can't crack a liquid. Or you can pour a liquid, but you can't pour a solid. So those are two different regimes. And going from one to the other here is just an incremental process in the temperature, but at a certain point it flips. The system flips from one regime, overall pattern, to another overall regime, a liquid. And that's a phase transition. They're normally driven by positive feedback, and this is applicable to all complex systems, not just a bacteria and a water here. It's also like political regime shifts is another example of this, right? Suddenly the system flips from a stable state to an unstable state, or the fall of the regime, or from one regime to another. And that's also a positive feedback loop. When we look at protests, for example, they're driven by positive feedback. More people that go out protesting, the better it is for you to go out and protest, because you're not likely to get caught or anything. And that's a positive feedback loop, and very quickly the system can flip from one regime to another. It's a phase transition. So this is actually taken from that paper, the one on self-organization. It describes how self-organization takes place, but now talking about feedback loop, it is a nonlinear positive feedback driven process. So positive feedback leads to an explosive growth, which ends when all components have been absorbed into the new configuration, leaving the system in a stable negative feedback state. So it's going again from a stable state at the beginning, but then we have self-organization and we have this positive feedback loop, and it's kind of a phase transition, and it takes it into a new regime where you have new stable configurations. That's called, the overall pattern is kind of called punctuated equilibrium. We have an equilibrium state and then positive feedback, and it takes us to another equilibrium state. And that's how complex systems change. They go through those, they can flip very rapidly from one regime to another because of the positive feedback. And so self-organization is a process. I mean, nonlinearity over time gives us this idea of chaos, sensitivity to initial conditions, the butterfly effect, we call it. And it's that idea: a butterfly flaps its wings in Brazil or somewhere, and we get a tornado in another part of the world. And the point is that the butterfly doesn't cause the tornado. The butterfly it changes some initial conditions, a very sensitive change to initial conditions that gets amplified by that positive feedback loop. And the idea is that because you have this feedback loop, you can have a very small change in input value to the system, and that can create a very big difference in the output value. It's like a small, they discovered this first in experiments with weather patterns, and it was really just a small change in a figure that they put into the computer, which then, computers do feedback loops, they do iterative processes, and it was really working to compound that very small change, which led to a very large output in the overall system over time. So that's kind of the essence of chaos theory and sensitivity to initial conditions, and behind that is the positive feedback loop. So we've talked about complex systems, we've talked about self-organization, and we've seen how that's kind of closely related to nonlinearity. Those two ideas are closely associated. We're going to talk about networks now. There's another feature of complex systems. They have high degrees of connectivity, and that gives them a networked structure. So this is New York transport system. Network science, network analysis, they become very powerful tools for many researchers. Actually, they've become very popular over the past few decades. They're used in many different areas now, particularly in social sciences, for social networks, spreading of diseases, and so on. But it's more than just a set of tools. It's also a way of kind of looking at the world, should we say. It's a relational paradigm. Networks are all about connectivity and kind of representing that connectivity that is the kind of architecture of a complex system. If you think about what a complex system looks like, well, it kind of looks like this. I mean, one person described it as that the architecture, the networks are the architecture of complex systems. I think it's important before you kind of start using all those tools, all those analytical methods, to kind of think in this relational way, because the network is it's based upon a relational paradigm. You're just looking at the connections. You're not looking at the things so much themselves. And it becomes relevant once you turn up the connectivity in the system. At low levels of connectivity, you got a simpler system, and it's really governed by the properties of the parts rather than the relationships between those parts. You turn up the connectivity, it becomes these kind of networks that shapes the structure and the feature of the system, and you have to kind of look at it in a different way. You have to look at it in terms of this connectivity, which creates a different kind of geography, a different kind of space. We're used to kind of walking around looking at what we call a Euclidean space, which is a three-dimensional space in which objects exist, and that's our usual kind of vision of the world. But this is actually a different way of looking at a relationship, way of looking at the world, creates a different kind of space. It's a topology. It's a topology of that network, which really defines how things play out in that network. If we thought about this as a logistics network, if you're a little packet there in New York, it might be easier for you or quicker for you to get to London rather than to go, London, which is maybe a few thousand kilometers away, than for you to go, a few hundred kilometers up into Canada. And that's because of the connectivity of the network. That topology shapes how things flow in it, and how close or far things are away from each other. And that's different from the traditional Euclidean view of space. And it's important to kind of start to look at systems in that way, in terms of that connectivity and how that connectivity shapes what could happen, how processes happen and flows happen on the network. So Emmanuel Castell's kind of points to that original idea that I was trying to make there, that it's more the structure of the network than the properties of the parts. So he says here, Emmanuel Castel is a famous sociologist. He's talking about, he wrote a book about the network society, and he had this to say: the logic of the network is more powerful than the powers of the network. So it's a very general principle, but it's a very important one. It applies in all situations where you turn up the connectivity, which is all complex systems. The structure of that network is going to define the properties of the elements in the system. So yeah, the rules and dynamics of the system change fundamentally as we go from low levels of connectivity to high levels. One way I like to illustrate this is that famous saying about it's not what you know, but who you know. At low levels of connectivity, it matters what you know, which is like the properties of the parts, properties of you. Do you know something or not? But if you turn up the connectivity, it's actually not so much what you know as your connectivity to that knowledge. So if you ask a teenager, maybe, what's the capital of say Poland? They would say, well, I know that, and they'd pull out their mobile phone, they'd Google it and say, yeah, it's Warsaw. You see, I knew the answer to that. And that kind of illustrates, right, they're super connected, so they don't need to know that knowledge. So there it illustrates how it's their connection in the network that actually matters, and their place and connection in the network that matters more than the properties of themselves, whether they know it or not. That's a very general principle. It applies to all complex systems and all networks, and it's important to have that awareness. But it's just, that's a general principle. Then you can start digging it. Once you kind of get that relational paradigm, that way of looking at the world, then you can get a much more powerful kind of analytical view of a system once you start to get your head around looking at it as in that relational paradigm. So this is a network. When there's many different ways to analyze networks, we have a whole course on this. I won't go into it too much here, but first question is, how connected is it? Things like average path lengths. How long does it take to get from one side to the other, which defines how close things are to each other, how connected they are. But we also want to ask, we might want to ask which element in this is very important. It might be like a social network, and we're asking which is the most influential person in that network. And you might just say, okay, it's the yellow dot there, the yellow node, which is true, they have a high degree of connectivity, but they might not be the most influential person there. Maybe all those people they're connected to aren't very connected to other people, and someone else is. And that kind of a measurement of how connected you are to people who are important is called eigenvector centrality, and that's just one way of measuring it. There might be another person there who's a kind of connecting between different groups, so they play a linking or bridging role, and that has some great importance. But there's many different ways of looking at it, and also you want to, looking at the network, you want to know how centralized it is or how distributed it is, the degree distribution. Are there some people who have lots of links and some people who have very few? These are the kind of structural properties to a network that define how things are going to flow through them. So in a centralized network, resources, information, and so forth will flow very differently to in a decentralized network. And there's just many different ways of analyzing a network. We won't go into all of that here. I think we're running out of time, but you can check our network theory course for all of that. So, adaptation, evolution, the final one we're going to touch upon here. So not all complex systems, but most are adaptive systems, complex adaptive systems. There's quite few that aren't, actually. I mean, the weather is an example of a system that isn't adaptive, but most of them, societies, economies, ecosystems, transport systems, and so on, are adaptive systems, and they evolve over time. And how those systems are shaped is a lot to do with how the parts adapt and interact locally. So you really need to kind of dig into that and try and understand it. It's a lot to do with the actual local logic of the agents in the system. And we could say this is the area of cybernetics, which is studying control or regulatory systems in mechanical, in technology, in animals like this, creatures, human beings, and so on. A thermostat is an example of a control system. It's regulating the temperature in a building. That actual model of a sensor and a logic device, a logical system, and an actuator that a thermostat has, that's the same basic structure to a control and regulatory system that we see in all kinds of adaptive systems in animals and humans and so forth. It's just a question of the kind of complexity of that regulatory system and the algorithms that they're using. They can be very simple, like in that thermostat, or more advanced, like this animal, or even more advanced, like in a financial market. These traders are actually doing the same thing. They're going through feedback process of regulation and control and optimization, trying to get the outcomes that they want, based upon algorithms or more advanced kind of schemas. And if we're talking about complex adaptive systems, we need to understand that to a certain extent, because it's a lot of what shapes the actual outcomes. What is the rules under which those agents are acting? But they're not just acting, they're actually interacting with each other. And this kind of brings us to the area of game theory. So game theory studies situations of strategic interaction between adaptive agents and kind of dynamics of cooperation and competition that emerge out of that. These agents in the system, they have their own agendas, their own goals, and they're interacting with others. Do they form patterns of competition or cooperation in that? That's what we're studying in game theory. What are the structures that lead to cooperation? What are those that lead to competition? So finally, we'll talk about evolution. Complex adaptive systems change on the macro level through a process of evolution. Like we said, there's no one in control in the center there, like in an ecosystem, telling all the plants what to do. But they still, as a whole system, they have to adapt, just like those agents in the system. They have to adapt to their environment, to a changing environment. We're all familiar with this from ecology, the notion of evolution. Complexity theory kind of abstracts this to make it relevant for all complex adaptive systems, economies, societies, political systems, and so on. So how does that work? I mean, it's the same process of adaptation. Evolution is the same process of adaptation. It's just operating on a whole population of agents, this time on a complex adaptive system as a whole in response to their environment. So evolution is the adaptive response of a group of agents that occurs over a period of many life cycles. The process of evolution involves a number of elements, including the production of variety within a population, the exposure of those variants to their operating environment, to see how well they perform within that context, and the selection and duplication of those variants that have proven most successful. So that kind of itemizes the different parts. There's the production of variety, they're exposed to the operating environment, and then those that are best adapted, best used to that environment are selected for and duplicated, and that's how a whole complex adaptive system, in such a way the whole system comes to exhibit more of the characteristics required for success within the given environment, thus managing to adapt without centralized regulation. So this is how a decentralized process of adaptation takes place across the whole population. And it's kind of an interplay between diversity and conformity. The system needs variety and diversity so as to create different possible solutions, but then it has to select from them and create conformity. It has to converge upon a certain solution that is optimal or best for that environment. So it kind of gets back to that general theme here around this interplay between order and disorder that we saw there in self-organization. It's captured in this term edge of chaos, an evocative term. Scott Page, in his book on complex adaptive systems, describes it like this: systems that are too simple are static, and those that are too active are chaotic, and thus it's only on the edge between these two behaviors where a system can undertake productive activity. In its most grand incarnation, the edge of chaos captures the essence of all interesting adaptive systems as they evolve to this boundary between stable order and unstable chaos. So, yeah, it goes back to the idea that self-organizing systems need a certain degree of entropy to be able to thrive and survive and self-organize, and that's the same for evolution. Evolution takes place on this kind of edge of chaos between disorder and order, where it can stay kind of generating itself over time. So that's the theory of complexity theory, and we just got to touch upon some of it there. We didn't get, certainly there's many aspects that we didn't get to touch upon. But I guess the question then is, like, how is this of relevance? I mean, it's highly abstract theory. How can it help us in the world that we live in today? And I came across this little quote the other day from Petra Kunkel. As she says, any sustainability challenges we're dealing with, they're actually a result of fragmentation of way of thinking. So we can take it one level up so that we can defragment the thinking, so that we can defragment the action. So this is kind of the general theory, general premise in systems thinking. A lot of the problems we have today surround our products of kind of our ways of thinking, our reductionist ways of thinking. And we need to change that to a more kind of holistic way of looking at the world. And it's really complexity theory that's helping us with this in many ways. At the moment, the only way we know how to do abstraction is through reduction of complexity. That's what kind of reductionism is about. It's what those linear models are about, the reduction in complexity, or externalizing that. If you want to do any kind of large-scale coordination in our worlds, we have to use abstraction, right? We have to, if we want large organizations, we've got to use models, and those models, at the moment, a lot of them are based upon kind of linear, simplifying assumptions. So, and we see it kind of out there in the world. The only way we know how to do large-scale coordination is through reduction of complexity. We can't really embrace it. We have these models that are very linear. They end up, our world kind of ends up looking a bit like this, which is a good expression of reductionism and linear thinking. Lots of lines. And this is how we do food. And we manage, getting back to this theme of kind of patterns and order and disorder, which is at the heart of complex adaptive systems. How do we create order in our world, right? Our organizations? Well, they look like this. We externalize the complexity. We externalize the nonlinearity. We push the complexity outside the boundaries of our organization And that's how we get order. We don't, and because of that, we don't have organizational structures that can deal with complex challenges that we face. That's a big problem we have at the moment, and changing all of this starts by understanding complexity. So if we want to change our organizations, change our way of responding, that's going to start by changing our way of thinking and really kind of embracing and, of course, understanding complexity, and that's what complexity theory is about. Okay, so that's the theory of complexity in as brief a time as possible. If you have any questions, I'm happy to discuss those. Okay, so we don't have that much time. We kind of run over time a little bit. I think that's about 50 minutes already. But we'll cover just a couple of questions then. Let's see what we have. Is complexity a requirement for emergence? It's kind of a difficult question. Its emergence is a product of self-organization, and we kind of itemize some of the elements there that you need for self-organization to take place, such as autonomous agents, adapting to local information, high levels of peer interactivity. So in a general sense, you could say yes, but yeah, for emergence, you have to have a decentralized system. There can't be someone in control, and you have to have high levels of peer interactivity. So what's the best way to work with complex systems for people without quantitative skills? So, I mean, there's more and more kind of educational stuff out there and information about complex systems that isn't quantitative. I mean, all our courses, you can take a look at those. They're non-quantitative. There's a lot of good books too. I cited there Scott Page near the end there in that book, Complex Adaptive Systems. He also has a course on complexity theory from the Great Courses, which is a really good one. It's non-quantitative. But yeah, if you take a look at our stuff, you'll find a lot there. So there's one question: why is negative feedback linear? So that's a slightly more difficult question. It was debated there for a while. I guess I'm talking quite a general sense when I say that it's linear. I mean, negative feedback creates equilibrium states because it's self-balancing, right? It creates stable equilibrium basins of attraction wherein we get linear behavior. If you look at any exponential nonlinear process of change, you'll see behind that is a positive feedback, not a negative feedback. Negative feedback holds the system in a stable state and gives incremental change. Positive feedback leads to exponential change, and that can be, it was discussed there about whether it's growth or decay. That positive feedback can be growth or it can be decay, right? It's just signifying that the rate at which the change is happening is increasing, is compounding upon itself. And that compounding, increasing rate of change happens through a positive feedback loop where more begets more. So all those exponential processes of change are positive feedback, and they're non-linear. And it's really best to, we didn't get time to touch upon it there, but to talk about it, linear non-linearity in terms of basins of attraction and equilibrium and non-equilibrium, the work that Prigochet did, that's the best way to think about it. And if you can get into all that, you can kind of explain better what I mean here by saying it's linear. It's quite a general statement, and it's best to kind of look at it from there. Obviously, we didn't get time to touch upon that. It's very interesting talking about basins of attraction as a way of looking at how complex systems evolve and change over time. Maybe we get an option to talk about that in the future. But yeah, we've already used up a lot of our time, so let's leave it there for the moment. I'm very pleased to give you this presentation. We've actually got another one coming up later on in the week on Thursday. We're going to be talking to Claude, who's going to be walking us through his methods for enabling systems change through using game models. And that is on Thursday, so that's our next live streaming event. Thank you very much for joining us, and I'll say goodbye.